I have a triangle here. It has a 90-degree corner, and I have some numbers and some letters on there to try and figure out what the angles are. And I'm going to start with my tan ratio because that's what we were doing the other day. Tan ratio would be the opposite over the adjacent. Now, if I were to sort of analyze this triangle, if I start at the 90-degree corner and I look across to find my hypotenuse, I will find a number there. And in the tangent videos, there was no length of the hypotenuse. You didn't know it. So this triangle is going to be a little bit different. If I look across from alpha, I will find this side. This is opposite to alpha. So I would be able to fill in a number there. That means that the third side, this one here, this is adjacent to alpha. And I don't know what that side is. So when I go to fill in this ratio, I'll have a number here, and I don't know that. Oh, sorry, I don't know a number there. I just have the opposite side. That's all I've got. Which means I've got the alpha still and the adjacent side unknown, because I can't use this ratio. I don't have enough information. So strike it from the record. Fortunately, there are two other buttons right nearby your tan button, the sine button and the cosine button. And those are just two different ratios for sides of triangles. So the sine ratio, sine of any angle, I'm just going to use an omega here, is the opposite side divided by the hypotenuse, and the cosine of any angle is the adjacent side over the hypotenuse. So these two ratios actually use a number for the hypotenuse, unlike the tan ratio. Difference between them, the second side you use for sine is the opposite side. The second side you use for cosine is the adjacent. So I'm going to solve alpha here first. Let's start with sine alpha. Well, if I look across the triangle, I already saw that 4 was opposite to alpha, so I'm going to put a 4 in for the opposite. And I know that 15 was the length of the hypotenuse. So I'm just going to do, well, I guess I can just throw the arc sine over there, right? Just like tan, I need the opposite of the sine function on that side. So I throw over that, pull an arc sine on the other side, and I will end up with arc sine of 4 divided by 15 is 15.466 degrees. All right. Now, if I go to do beta, so I'm going to try and solve the beta angle. Notice that I don't have the opposite side. If I look across, that's my opposite to beta, and it's blank. So I'm not going to be able to use the sine ratio for beta because I don't have the opposite side. I'm going to have to use the cosine ratio because I do have the adjacent side. So cos of beta would be the adjacent side over the hypotenuse. Now, do you notice that these two things, it's the same fraction? And that's why there are sine and cosine, right? When you use that prefix, it means with, right? So you've got the sine ratio, which uses this fraction to get one angle, and then this angle has a partner, right? Whatever's left to fill in the triangle, so the related sine ratio, or the cosine ratio, will give you the size of that other angle using the same fraction. So toss it over. together, going to get arc cos, shift cosine of 4 divided by 15 gives me 74.534, if I round it, degrees. And if you were to check, add this to this, 0.534 and 0.466 are going to niche together to make 1. 74 plus 1 would be 75, plus 15 gives you 90 degrees. So it worked out just so. So if you've got a triangle where the hypotenuse has a number on it and only one of the other sides has a number on it, instead of using the tan ratio, it's more convenient to use these. So you could, if you wanted to do a lot of work, use the Pythagorean theorem to calculate the length of that side. Then you would have it, and you could use your tan ratio if you wanted to. But that just creates more work. When you already have buttons on your calculator to do this, and if you can set up opposite over adjacent, then you can definitely set up opposite over hypotenuse. It's not that hard to figure it out. So I'm going to clean this off, and we will try an example of finding sides, and then I think you're good for the practice problem. Okay, so I have a triangle here where I know one side and I know one angle. So I'm going to use sine or cos in order to figure out the lengths of the other sides, but I have a little bit of labeling to do. So I'm going to find my 90-degree corner and look across. That means this is my hypotenuse. I'm going to look across from the 36-degree angle, and I'm going to find my opposite side, which is unlabeled. So I'm going to put a letter in there just so we have something to fill into our formula. So I'm going to put in an A there. Why not? If that's the hypotenuse and that's the opposite, then this must be the adjacent side, and I'm going to put a B there. Okay. So if I start with these ratios, the sine ratio, sine of any angle is the opposite side over the hypotenuse. And I start filling stuff in, I can see that sine of the 36-degree angle would be the length of the opposite side, that's this unknown, divided by the length of the hypotenuse, which I do know. Sine 36 I can just get from a calculator. Sine 36 gives me 0.588 if I round it. And just a little bit of algebra to finish. I need to break this division, so I'm going to multiply by 21. And on the left side, I get 12.343. So the only way for this angle to be 36 degrees and the hypotenuse to be 21 is if this side is 12.343. Now if I want to use the other one, I notice that I don't have the opposite over here, I have the adjacent. So instead of using the sine ratio, I'm going to use the cosine ratio, the one that goes with it, to find that other side. So cos of any angle would be the adjacent over the hypotenuse. So cosine of 36 will be B, the length of my adjacent side, divided by my hypotenuse. So we're going to hit cos of 36. And I get 0.809 equals B over 15. Oh, my brain is in the last example. The length of the hypotenuse is not 15, it's 21. Dummy. there. So I'm glad I caught that. So to fix this division by 21, I need to multiply by 21. 0.809 multiplied by 21 gives me 16.989 if I round. So the only way for this side to be, the hypotenuse to be 21, and this to be a 36-degree angle, and this to be a 90-degree angle, is if this side is 16.989 units long. So by using the sine and the cosine ratio together, you're able to get both of these sides for that particular triangle without having to do any extra work. I'm going to clean that off. We'll try one more example where we don't know the length of the hypotenuse, and then I think you're good for the practice problems. Okay, so I've got a triangle here. I'm going to look across from my 90-degree corner. That's where my hypotenuse is. I'm going to look across from the angle I know. That's going to be my opposite side, opposite to 25 degrees, which means the side that's left is my adjacent side. Okay. So I've got these two new ratios here. I've got the sine, the cos, and the tan, which we've already rejected tan because we don't know the adjacent side. So let me just write them out here. Sine of any angle is the opposite over the hypotenuse, and the cosine of any angle is the adjacent over the hypotenuse. So if I start filling numbers into this, right, sine ratio would be sine of 25 is the length of the opposite, which I have, that's 8, over the length of the hypotenuse, which I don't have. So I'm just going to put in a C there to represent the length of the hypotenuse. And I'm just going to leave that for a minute. If I try filling in the cosine ratio, cosine of 25 is the length of the adjacent side, which I don't know, so I'm just going to put a B there, over the length of the hypotenuse, which I don't know, so I'm putting in C there. Now, if you look at the information you've got, I have exactly one letter in this expression, so I can actually work with that expression. In this one, I have 2 letters. There's 2 unknowns, so I'm not going to be able to work with that. I don't have enough information. So for this particular setup, the sine ratio is going to let me calculate the length of the hypotenuse. So how do I finish this algebra? I need sine 25 as a number, 0.423 if I round it. And I've got that weird upside down thing. Right? This happened when in the tan ratio video where I had something in the denominator. In the tan video, you were able to just swap to the other angle. But in both of these triangles, the hypotenuse, or both of these ratios, the hypotenuse is in the denominator. So switching to the other corner isn't going to make a difference. I'm going to have to move this C up here. So I don't like divide by C, so let's get it over here. And then to finish, I have a multiplication there I need to break, so I'm going to divide by 0.423, which gives me C is 8 divided by 0.423, and the handy calculator, 8 divided by 0.423 gives me 18.913 if I round. So the only way for this side to be 8 and this angle to be 25, and this angle to be 90, is if the length of the hypotenuse is 18.913 units. Now that I have that, I could fill that in here. And now I have enough information to actually use this ratio. So I can take cos 25, gives me 0.906. I round to 3 decimal places. And to get the b by itself, I'm going to have to multiply by 18.913, which gives me 17.14. 141 if I round to 3. So in this particular example, the sine ratio was able to find the hypotenuse for me, and then its partner ratio, the cosine, once I had that hypotenuse, was able to spit out the adjacent side. So together, those two ratios allowed me to solve this entire triangle. I now know the length of every side. So that's it. You've got two new ratios to work with. One is opposite over hypotenuse, the other is adjacent over hypotenuse. You're still plugging into calculators to get decimals, and they're still solving sides or angles with them. So it's very similar to the tan ratio. So I think I'm going to clean this off and let you head to the practice problems.